Hello everyone, welcome back. This particular video is going to focus on the nucleophilic aromatic substitution reaction of aromatic compounds. Now this is different from the electrophilic aromatic substitution reaction. In an electrophilic aromatic substitution reaction, the aromatic compound reacts with an electrophile, and the aromatic compound itself acts as the nucleophile. But in a nucleophilic aromatic substitution reaction, the aromatic compound reacts with a strong nucleophile, which means it itself acts as the electrophile here. So the roles are reversed compared to an electrophilic aromatic substitution reaction. So a very classic example of this reaction is captured here, which is the reaction of para-bromonitrobenzene with sodium hydroxide. Now going back to substitution reactions, recognize that sodium hydroxide is an ionic compound, and so this hydroxide here is a strong nucleophile. So the hydroxide is a strong nucleophile. So when we react this para-bromonitrobenzene with sodium hydroxide with some heat followed by an acidic workup, we get this para-nitrophenol compound. And overall, when you look at it, what happened is that the bromo group here has been substituted by the hydroxide. So the bromine here is behaving as a leaving group. So this is reminiscent of an SN2 kind of reaction where you have an alkyl halide, you react that with a strong nucleophile, and you get a product out of that. So for such a reaction to take place, there are some criteria that must be met. The first one is that the ring must contain a powerful electron withdrawing group. And a good example is the nitro group. So in this particular example, the ring contains an electron withdrawing group. So we do have an electron withdrawing group here and a very strong electron withdrawing group. The second is that the ring must contain a leaving group, which is usually a halide. And so we have the leaving group in this particular example. And the third and the most important criteria here is that the leaving group must be ortho or para to the electron withdrawing group. So notice in this particular molecule, the relationship between the leaving group and the electron withdrawing group is para. So that is very important, because if we have a similar compound, an isomer of this molecule, and let's say we have meta-nitrobenzene or meta-bromonitrobenzene, and if we conduct a similar reaction where we react this with sodium hydroxide, temperature follow with an acidic workup, because the relationship here is meta, we will not get a reaction here. So there is no reaction under these conditions. So it is very important that the relationship between the leaving group and the electron withdrawing group is para or ortho to each other. So the mechanism of this reaction, the nucleophilic aromatic substitution reaction, involves a few steps. The first step is the nucleophilic attack on the aromatic compound. So we start with our aromatic compound, and the nucleophile, which is the hydroxide ion, this will attack the alpha carbon, so to speak, here. Okay, and that would be the carbon which is connected to this leaving group here. You can call that an alpha carbon. So the hydroxide goes and attacks that carbon. So as that attack happens, because there is a pi bond here, that pi bond gets pushed away, okay, because that carbon does not want to exceed its octet of electrons. So this is going to give us an intermediate where we have the bromine and the incoming nucleophile, which is the hydroxide. So we have the leaving group and the nucleophile connected to the same carbon. And there should be a negative charge on that carbon, the ortho carbon where the electron pair went, and pi bonds here throughout. So if we look at this complex here, this is similar to the sigma complex that we see in an electrophilic aromatic substitution reaction. The difference is that the sigma complex has a carbocationic nature, while this is carbanionic in nature. So this is a carbanion. And this complex is called a Meisenheimer complex. This is called a Meisenheimer complex. Now, very similar to the sigma complex, the Meisenheimer complex here is also resonance stabilized. So we can draw a few resonance forms for this Meisenheimer complex. We can use that lone pair and push the electrons around. So we will get to the next resonance form where the negative charge is on that para carbon next to the nitro group. This double bond is still there. This negative charge moves around again. We can push this over, get hydroxide, Br, double bond here, negative charge over there, nitro group is here, and we have the negative charge over there. And from this particular resonance form, or from any of the other resonance forms, we're just trying to show the resonance stabilized nature of this Meisenheimer complex here. But from this particular resonance form, we can bring those electron pairs down here and kick out the leaving group. So the leaving group can be lost at that point. And so this is going to bring us to the product where we have the nitro group and the hydroxide over there, double bond, and double bond. So that brings us to the product. Now, if we look at these resonance forms, we see the reason for why we need an electron withdrawing group here. And also why that electron withdrawing group should be ortho or para to the leaving group. So what we see in these resonance forms is that the negative charge, the carbanion that's generated, lands on the ortho, para, and the ortho carbons. So when we have an electron withdrawing group, a strong electron withdrawing group like nitro at one of these positions, or if you can have more than one, that's even better. So when you have an electron withdrawing group at one of these positions, it is able to stabilize that negative charge. Because if we draw out the Lewis structure for nitro, what we will see is that we are able to draw additional resonance forms here. So from this particular resonance form, we are also able to draw an additional resonance form where we use this negative charge to the nitro group and delocalize it into the nitro group. So the nitro group being strongly electron withdrawing, it's going to inductively stabilize that negative charge. That means it's going to help stabilize the negative charge by pulling the electron density away from the ring. But additionally, it can also do resonance involving that negative charge to give us a resonance form, an additional resonance form like this. So that makes this Meisenheimer complex stable. And this can only happen if the nitro group is located on one of the positions where the negative charge ends up. And those positions are ortho and para. So the negative charge lands on ortho and para positions. So that's why we need the electron withdrawing group at the ortho or the para position. Now, at this point here, when we make the product, recognize that this reaction mixture is still basic because we're doing the reaction in presence of a base. So the product that we generate here, this can be deprotonated by the hydroxide, which is our strong base. And the phenol is acidic. So in principle, what's going to happen is that the hydroxide is going to deprotonate this product that we made. And it would give us the conjugate base of the phenol, which is the phenolate ion. So we'll get the paranitrophenolate ion. So this paranitrophenolate ion needs to be reprotonated to get the product. So that's why we do the second step, which is the acidic workup. Because when we take this paranitrophenolate ion and we do an acidic workup on it, then we are reprotonating that phenolate or putting the proton back on the phenolate. And so that would give us the product where we have the phenol and not the phenolate. So that's how we get the product here. Now, again, notice that I moved around the arrangement of the pi bonds here, but that really doesn't matter because this form and that form are just resonance forms of each other. Either one represents that molecule. So that's the nucleophilic aromatic substitution reaction, which involves the reaction of an aromatic compound with a strong nucleophile. Important things to keep in mind is that you must have a strong electron withdrawing group in your aromatic compound, which is either ortho or para to the leaving group, which is a halide. And it involves the formation of this resonance stabilized Meisenheimer complex, which is basically a carbanion equivalent of a sigma complex that we've seen in the electrophilic aromatic substitution reaction. I hope you find this video helpful. Bye.